Ever wonder how computers can see the 3D shape and material of an object just from a flat photo? It's like magic, but it's actually science. Today, we're diving into a breakthrough in inverse rendering, a field that's unlocking the secrets of light, surfaces, and how we can recreate the real world in digital form. Let's start with the basics. Inverse rendering is all about reverse engineering the hidden properties of real-world objects from images. Think of it as solving a puzzle where the final picture is a photo, and your job is to figure out the shape, texture, and how light interacts with the surface. But here's the problem. Without the right tools, it's like trying to solve a jigsaw puzzle with half the pieces missing. Traditional methods rely on bulky, expensive setups, like giant light stages with hundreds of LEDs. These systems are powerful, but they're not exactly something you can set up on your kitchen table. Enter display-based inverse rendering, a smarter, more accessible approach that uses your phone or computer screen as a programmable light source. Here's the trick. LCD screens emit polarized light, which acts like a superpower for separating light reflections. Imagine light bouncing off a surface in two ways: diffuse reflections, like a matte wall scattering light in all directions, and specular reflections, like a mirror bouncing light directly back. By manipulating the polarization of light from a screen, researchers can tease apart these reflections, giving them a clearer picture of an object's material and shape. But here's the catch. Until now, there was no real-world dataset to test these methods. That's where this new breakthrough comes in. Created by researchers from POSTECH and Meta, this dataset is the first of its kind. It captures real objects under controlled display lighting, using a system that combines an LCD monitor with stereo polarization cameras. Think of it as a 3D scanning setup that uses your screen as a light source. The team illuminated objects one light at a time using OLAT patterns, a fancy term for precise light sequences, while the cameras recorded how light interacted with surfaces. But this isn't just about taking pictures, it's about creating a treasure trove of data. Each object was also scanned with high-precision 3D scanners, giving researchers a gold standard to test their algorithms. And here's the kicker. The dataset lets you simulate new lighting conditions by mixing captured images. It's like having a virtual lighting studio where you can tweak brightness, angles, and even add real-world noise. Of course, there were hurdles. LCDs don't turn off completely. They have a faint backlight that can mess up measurements. The team calibrated this by using a sphere with known properties, adjusting parameters until their system matched real-world data. They also tackled the nonlinear way screens map brightness values, ensuring their dataset is as accurate as possible. When they tested existing inverse rendering methods on their dataset, they found old approaches struggled with display-specific challenges like polarization and near-field lighting. But they also introduced a simple new baseline model that outperformed previous techniques, proving that display-based systems can match traditional setups without the bulk. The real breakthrough. A new dataset that's a goldmine for researchers. It's not just about shape. It includes precise geometry, 144 superpixel positions, and stereo views of 16 objects. Imagine having a digital twin of a sculpture, where every crack and curve is captured with millimeter precision. But here's the kicker. It's designed for inverse rendering, a process that rebuilds 3D scenes from 2D images. Think of it as reverse engineering light. Here's the trick. Traditional 3D scanning captures shape but not light. Think of it like taking a photo of a car. You see its outline, but not how the paint shimmers in the sun. That's where photometric stereo steps in. By analyzing how light bounces off an object under different angles, researchers calculate something called surface normals. Basically, the direction every tiny part of the object is facing. It's like mapping a mountain range using shadows. But here's the twist. Real-world objects aren't perfect. A ceramic bowl reflects light differently than a piece of fabric. To tackle this, scientists are blending old techniques with AI. Take differentiable display photometric stereo. It's like teaching a computer to see materials. By training neural networks on thousands of light reflections, the system learns to distinguish between a glossy surface and a matte one, even if the object is complex or transparent. This isn't just a better scanner, it's a leap forward. Traditional datasets focus on specific tasks, like measuring depth. This one, it's an all-in-one toolkit for tackling complex lighting, materials, and even near-field effects. It's the digital equivalent of a lab bench, where new techniques get tested and refined. So next time you're dazzled by a movie's realism or a virtual try-on experience, remember, it's powered by datasets like this and the science behind them. And if you're curious how it all comes together, stay tuned. We're about to dive into the AI magic that turns these clues into digital wonders. Thanks for watching. If you want to see how this data becomes art, hit subscribe, and let's keep exploring the science behind the spectacle.